If you recall, we left off yesterday looking at simulation, right? And we were looking at this example where, what was it? Alex claimed he was a 75% free throw shooter. Gabriella watched him shoot a set of 53 throws. He shot 60%. And so now the question is he truly a 75% free throw shooter and that was just a fluke, or is he not truly a 75% free throw shooter? And so we looked at one option here. We talked about using random numbers to investigate Alex's claim. I mentioned that you can use a calculator to do that. You can use a spreadsheet to do that. I can show you how to do that sometime if we get a chance. I don't think you have to be able to do that for homework, so it's not something where you have to be able to randomly generate the numbers, but we can look at that. And if you recall this situation, 100%. So it was picking numbers between 1 and 100. Since he claimed 75%, 1 to 75 is going to represent when he makes a shot, successes. 76 to 100 is the other 25% of the time when he misses the shots. Okay, so on this one, we came up with that in this simulation, it represented 78% success. But that's just one simulation, isn't it? Just like his 60% shooting was one set of 53 throws. And so what we were getting ready to look at here is, okay, what happens when we put multiple simulations together? Okay, so this is how many successes out of 50 trials. And I will say, if you count up the heights of all the bars, there are 100 total samples in this histogram here. Okay, so this is doing 100 simulations of 50 shots each. Okay, so the success out of 50 trials is he takes 50 shots at a time, or there's 50 shots generated at a time, I guess I should say. Okay, the fact is, if you add the heights of all these bars up, this histogram represents this happening 100 different times. Okay, so 100 sets of 50. Now, the idea here, what we're trying to do is we're trying to look at, as we look at this histogram, okay, what is a reasonable range? We looked at ranges a little bit yesterday, but what is a reasonable range that if he's within this reasonable range, we can say, okay, yeah, that was a fluke, he either shot high or low, but that would be within range of 75%. And that's what we're trying to look at. I don't know how well you can see it, but it's there. As you look at this histogram, do you see a specific curve? Okay. I know there's a little dip in there, but you need to be able to be kind of, be willing to accept it's not going to be perfect, but can you see the normal distribution curve there? Okay, it's there, and it's the idea that, it's starting low, it's getting higher, and then it's going lower again. Yes, there's going to be some dips and stuff. That's part of normal distribution. That's fine. Okay? And we talked about normal distribution. What did we look at? Where is the majority of the information? In the middle, what percent? Middle 95%, right? And so that's what we're going to be looking for here is, where is the middle 95%? What is this acceptable range? Okay, he's claiming that he can shoot right here, 75%, because what is 75% of 53 throws? Because he's saying he's a 75% shooter. And so what is 75% of 50? Do the math on the calculator, and 0.75 times 50 is going to give me 37.5. So in order to be a 75% free throw shooter, he needs to be able to consistently make 37.5 shots, right? And so that's what this is representing right here in between the 37 and the 38 bar. This is where 75% falls. Because realize that this is not 30%. This is 30 out of 50 trials, right? I think I forgot to go in and explain that. But so this 30 out of 50 shots is actually 60%, right? So what this is saying is that there are, 3 of the trials that were at 60%. Then it looks like there were maybe, 2 trials? That bar is too high. that bar would represent 31, so 62%. The 32 bar is 3 high, so there were 3 trials where that would be 64%, so on and so forth. Okay. What did we talk about? 95%. If it's middle 95%, there's 2 ways we can look at this. One, the middle 95% usually falls where? The middle, except for the last little tails, right? So, and it works out this time. I'm going to show it, but if you look at all but the first and last bar, okay, that does work out to be the middle 95%. And my reasoning, I said that these bars represented 100 samples, yes? If you add up all the heights of the bars, you'll be at 100 samples. What is 95%? Or if 95% of the samples are included, how many samples would not be included? 5, right? Because if 95% of 100 is 95, then it's the 5%. Well, what just so happens, there's about how many samples down here in the 30 bar? Looks like 3. How many samples up here? Is that 1 maybe? That's 4. I was thinking it added up to be 5, but it's close there, right? And that's the idea. It's not going to be exact, but if you take off those N2 bars, your middle 95% is going to be in between there. Now, what are we in between? What are the endpoints for this 95%? So what is that point right there? It's in between 30 and 31, so it would be 31. That would be 31 out of 50 shots. And what is 31 out of 50 shots as a percent? 62%. What about the other end? It's in between 43 and 44, right? So that is 43 out of 50 shots, which is 86%. So based on these trials, okay, if a 75% free throw shooter is in a reasonable range, what is that reasonable range going to be between? It's going to be between 62 and 86%. Does that make sense? Okay. Now, what does this mean about Alex and Gabriella? Alex claims he's a 75% free throw shooter. Does his 60% success rate while Gabriella was watching him make that true? No. Okay. 60%, while just barely, it is outside of the acceptable range. Okay. So by shooting only 60%, that's saying, he's probably fudging a little bit. He's probably not exactly a 75% free throw shooter. Okay. Because whether it's a bad day or an extra good day, he should be able to fall in the range of 62 to 86%. Okay? Now, I'm going to write down some of this information over here. Let's see. What do I want to say here? So I'm going to mention 95% of the data is approximately 95 of the 100 samples. Oops. Okay, so since 95% of the data is approximately 95 of the 100 samples, that means 95%, what do we say, falls between 31 to 43 successes. So 95% of the data falls between 31 and 43 successes. Which is 62 to 86%. Okay. Based on our simulations then, the reasonable range is 62, reasonable range of means is 62 to 86% for a 75% free throw shooter. Gosh, tongue-tied. So based on the simulations, the reasonable range or reasonable interval of means is 62 to 86% for a 75% free throw shooter. And then all of that to say, Alex is likely not a 75% free throw shooter. And if you want to tack on there, he's likely not a 75% free throw shooter since he shot 60%. Obviously, you're going to write as little or as much of that information you want, but trying to get the basics there. Okay. And sorry, I know it's a lot of writing, but I don't know how to just put down work, you know. It's hard to put down work without some explanation here. Okay. Out there. When you flip over to the next page, we just have two quick questions we're going to consider before we go in and talk about margin of error. As you look at the top of the next page, the question is, how would your conclusion differ if you did 100 simulations of 10 shots each? Okay, so realize we did 100 samples, or if you will, 100, maybe I should use the word simulations here. Okay, we did 100 samples or simulations here. These were of 50 shots each, right? So now the question becomes, how would your conclusion differ if you did 100 simulations of 10 shots each? What do you think would happen? It'd be what?
Better.
What do you mean by better? Huh?
His percentage would be better.
Do we know that?
Well, I feel like my first 10 shots are better than my last 10 shots, so I feel like his percentage.
Okay. I wasn't thinking that. That's why I was curious how you were getting better, or what you were thinking better there. So you're thinking the more shots you shoot,
Arms get tired.
arms. Okay. So, whereas my brain was just looking at the first shot is equal to the last shot. All shots are the same. I guess that was kind of how now, and here's the deal. These are simulations, yes? So, if I throw into the fact it's a simulation, the first shot is just as good as the last shot, correct? Okay, so let's look at that aspect. So now, if we take out the issue of muscle fatigue, if you will, okay? It's simulated, okay? What is it when you guys play 2K and all that? You know, it's simulated. They don't get tired, do they?
Yeah, they do get tired.
Yeah,
Do they?
Yeah,
Okay.
they do get tired.
Okay. So, with that in mind, still 100 simulations, but 10 shots instead of 50 shots. So we have a smaller sample size here, right?
Yeah.
What's going to happen with a smaller sample size?
Would the percentage be like less accurate?
Yeah. We don't necessarily know if it's not going to necessarily be like a higher percentage or a lower percentage because that's going to be random, but it's going to be not as accurate. Okay? When you don't have as many of those numbers to repeatedly look at, it's not going to be as accurate. So what I'm looking for here is the smaller the sample size, the smaller sample size will make the results less accurate. Smaller sample size will make the results less accurate. What about the second one? It's still 100 simulations, but this time 1,000 shots. Should be more accurate, right? The larger a sample size, the more accurate those results should work out to be. Okay. So I'm going to say larger sample size should increase accuracy. Okay. One last big topic. And I think you'll like this because it's more mathematically based. Or at least, you know, it works better for me that way. We can pull out the calculators. And so the last concept we're going to talk about is margin of error. And that's kind of what we've already been talking about, right? Is, you know, that if here's the middle, what is that range that is acceptable? Okay, so if you're a 75% free throw shooter, what is that acceptable range? Okay, well, that acceptable range, the idea here that we've worked up to is margin of error. And go here. According to the empirical rule, if you don't remember that vocabulary, that was our normal distribution curve where we had the 68%, 95%, 99.7%. That was that empirical rule there. And according to the empirical rule, 95% of the values in a normal distribution fall within 2 standard deviations of the mean. Remember, we had 1 standard deviation at 68%, 2 standard deviations at 95%, and then 3 standard deviations with 99.7. So 95% of all sample results fall within 2 standard deviations of the population parameter being evaluated. That's the reason we've been looking at 95%. The margin of error gives the maximum expected difference between the sample result and the population parameter. So the mean or whatever that center point is. So the margin of error is, okay, how far below and how far above is a reasonable range. We have 2 different formulas to use here, depending on the situation. Quantitative data. So, you know, you have a list of values or something, you're given a mean, looking at what is that acceptable range. That's going to be your quantitative data. The margin of error there, 2 sigma divided by square root of n. You remember using sigma earlier this chapter? Sigma stood for standard deviation, right? Sigma was your population standard deviation. N is the sample size. How big is that sample? And then if your data is more categorical, so breaking something up into categories, then our margin of error is going to be 1 over the square root of n, where n is, again, the sample size. Okay. Let's look at our example. The College Board recently reported that the mean score on the SAT mathematics exam is 508, with standard deviation 121. Washington High believes that its seniors score considerably higher than the national average. So the school randomly sampled scores from 200 seniors, finding a mean score of 550. Is Washington High correct in its belief? So basically, do the numbers, does the data support the claim that their seniors, what was it? Score considerably higher than the national average. That's what we want to know. Are they correct in their belief? So, in order to do this, we need to look at the fact the College Board mean is 508. Theirs is 550. Is that high enough to say that they score considerably higher than the average? Or is that just within that reasonable range around the average? You see what I'm saying there? So if it's in that reasonable range around the average, they're not really scoring considerably higher. In other words, if I say, oh, well, our school got a 509, we're above average. Okay, 1 point. You know, that's not 550. Is that enough to say, yes, we are way above average? And that's what we want to decide. So in order to look at this, guess what? We're going to find the margin of error. Thoughts on which formula to use? The quantitative one. And I'll give you a hint, guys. And for the most part, I think it's held up to be true. If they provide you a standard deviation number, you're probably going to be using the quantitative one. Valid enough, right? If they don't provide you a standard deviation, you can't use that one. So just kind of a heads up. So we're going to be using the 2 sigma over the square root of n, because we are using the quantitative is what I think I should be saying, but what is sigma? The standard deviation, which is 121, so 2 times 121 divided by the square root of, what is n? Sample size, which is 200. Okay, told you need your calculators. Here we go. Do the math on the calculator. Make sure you don't make silly mistakes. 2 times 121 divided by the square root of 200. Okay. I know it's 17 point something. 17.11. Now, I'm only writing down a whole number answer, which is why I only remember it being 17, because our means are whole numbers, right? So I'm only going to use this as 17. So not disagreeing with the 17.11, just I don't need the decimals in here. Okay, so that is our margin of error. In order to find that acceptable range, we're going to take the mean and go plus or minus the margin of error. Okay, and we're trying to find the acceptable range. So which mean am I using here? Which one? The 508. Okay, this is your mean. So we're going to use the 508 plus or minus the margin of error of 17. So what is that range then? In other words, what is 508 minus 17? What is 508 plus 17?
525.
Okay. So 491 to 525 is our acceptable range. In other words, if the average score is 508 and your school scores from you score from 491 to 525, you can consider yourself within that average range. Okay, so this is what I'm going to call this my range of reasonable means. In other words, it's in that acceptable margin of error. Now, we need to answer the actual question. Is Washington High correct in its belief? Are they, what was their wording? They believe they scored considerably higher than the national average. 550 is above that 525 by a decent bit even, isn't it? Okay, and anything above that is going to agree. So, yes, Washington High is correct because 550 is above the range. You can write however much or little of that you want. Yes, because 550 is above the range. I think I'll just write it as that. Okay? Second part when you're ready. A random sample of 100 Washington High seniors reveals that 40% plan to take the SAT this year. Use the margin of error to predict the actual proportion of seniors planning to take the exam. Okay, so they're telling us to use the margin of error, which means we're going to have to find the margin of error, yes? Which formula am I using? Okay, and why are you going to say categorical? Okay, there is your big hint, guys. And I feel like in a way I'm giving you a cheat, but you guys are going to figure it out on your own. There's no standard deviation provided. Now, why is it categorical? Because it's 40% of what? Seniors, right? So it's the idea of categorizing by freshman, sophomore, junior, senior. Thus, it's categorical data. Okay? So, we're going to use the idea of 1 over the square root of n, which is 1 divided by the square root of 100. So my sample size is given as 100 this time. What is this 1 over the square root of 100?
0.1.
Okay. 1/10 as a fraction, which is 1/10 as a decimal, 0.1. Okay. Now, based on the fact that they gave us a percent, I would suggest that we might want to turn this into a percent. Because when we're trying to find our range here, based on our margin of error, what is 0.1? That is 10%, isn't it? So our margin of error is 10%. So what is the actual proportion of seniors planning to take the exam? How are we going to do that? Yeah. They gave us 40%. The random sample says 40%. So 40% plus or minus that 10% margin of error. Okay? And that gives us a range of 30 to 50% of the seniors plan to take the SAT. Okay. Get what you need there. And then there's, I think what? 2 quick questions on the back. You can probably start working the first example if you want. Find the margin of error for a sample with a standard deviation of 54 and a sample size of 450. So what's my formula I'm using to find the margin of error? Yep. Quantitative one, which is going to be the 2 sigma over square root of n. And here's the deal. They didn't really give us any information about what we're talking about, whether it really truly is quantitative or categorical, but they gave us a standard deviation. So assume that that's the one you should use. So 2 times what? 54 is my sigma, divided by square root of 450, because that is my sample size. So do the math, and what do we get? 5. If you do give me a couple decimal places this time, okay, 5.09. And we're not doing anything more than that with this one, so if I had a mean or something to add or subtract this to, we, might decide if we need those decimals or not. But so the margin of error is at 5.09. Now, don't be surprised. I don't know if they just ask you for margin of error, how it would be written, but don't be surprised to see it as plus or minus 5.09. Just the idea that, that you're adding it, you're subtracting it. It's that margin of error on both sides. And one last question to think about. Suppose the sample size was decreased. How would that affect the margin of error?
Would it increase?
Why?
Because again, the less samples, the least accurate it is, so you would have to have more room for
Okay, that's one good reason to support it.
You're divided by something small.
And that's the other good reason. Okay, either of those reasons we can argue, and they are supportive. So Chloe is saying, okay, if the sample size is decreasing, that's like the earlier going from 50 shots to 10 shots. If that sample size is decreasing, then that means it's less accurate, so I'm going to have a larger amount of error. Okay. The other thing is, look at what we just did. The sample size is what we were dividing by, yes? So if you decrease that sample size and you're dividing by a smaller number, the result of that fraction is going to be a larger number. So whichever way you want to think about it in your head, both are true. But yes, decreasing the sample size will increase the margin of error. Okay. I think there's only 12 questions in homework. I only had like 14 to pick from, and I got rid of a couple that I absolutely could not tolerate. Some of them are going to go right along with this, with margin of error and whatnot. Some of them you're going to have to think a little harder on, work a little harder on, but I think I got all the problems. I feel like you can do them. Okay? So let me know if you run into questions.